So, hello everyone. Good afternoon to those people who attend our seminar from Asia, or good evening, maybe even. Good afternoon. I see Sergei Shari to Novosibirsk. And yes, maybe even good morning to those of you who are situated in North America. And hello everyone to today's presentation of Jitao Li. Jitao Li received his combined Bachelor of Science degree, first of all from the Nanjing University of Aeronautics and Astronautics in China. And that was a double diploma program together with the Kharkiv University in Ukraine. And he was after
the presentation. And today my topic is vulnerability analysis and attack detection for subophrasic systems by using a zonotopic approach. This is a joint work with Professor Wang Zhenghua and Professor Shili Hua. Okay, I will briefly introduce this topic by six parts. At first, I will briefly introduce why I do this research, and then I will briefly introduce some preliminaries. That is what's the subophrasic systems I use. Will show how I use zonotope to do the vulnerability analysis of the zonotopes, and followed by do the attack detection using zonotope. And finally, I will show what's the performance by using zonotope to do this research, and finally conclude by with a conclusion. Okay, let's go to the first part, introduction. Okay, since in this talk we are concentrate on the subophrasic system, then one problem arising intuitively is what's the subophrasic system? Subophrasic system, by its definition, it refers to a new generation of system which consists of computation, communication, and the physical process. Okay, as we can see from this figure, the last page. Yeah. From this figure, the upper hand is the physical process, that is the actuator, plant, and sensors, and by lower, it is the controller, observer, and the detector. This is a remote computation, and they are connected by using network. This network is a computation part. Subophrasic system has various application fields. For example, autonomous driving and smart building. As we can see, both of these fields are safety critical fields. So security is very important for subophrasic system. Since security is very important for subophrasic system, and one of the main issues for subophrasic system is attack. It means an attack means some adversary signals injected by adversaries, and the motivation behind the attack may be finance or terrorism. And one of the most famous example is called Stuxnet, which happened in 2010 on Iranian nuclear facilities. And at that accident, it led to almost 1,000 Iranian enriching centrifuges destroyed. Obviously, it led to various economic loss. So to avoid such catastrophes, system vulnerability analysis and attack detection are very important. And these are also our today's topic. So, system vulnerability, it means the system for potential stealth attacks. And there are three dimensions for analyzing vulnerability analysis. The first is it possible for a subophrasic system to be destroyed by potential stealth attacks? And second, how to verify the safety of subophrasic system for potential stealth attacks. And finally, if a CPS is not safe, how can we evaluate the degree of the threat of potential stealth attacks? And then we are going to do some research on the attack detection. And attack detection means the strategy to detect specific attacks. And generally, there are three types of attacks. There are delay of service attack, and replay attack, and false data injection attack. And in this talk, we are focused on replay and false data injection attack. And the tools we are used is Zonotope. Zonotope is one of the methods of reachability analysis. So compute a set which includes all possible state values based on available information, and they can be divided according to their geometrical representation. There are mainly three kind of sets. There are polytope, zonotope, and ellipsoid. Both of all of them have their pros and cons. For example, by using the polytope, the set representation is very accuracy, but it can be very complex. On the other hand, if we adopt the ellipsoid, this set representation is very simple, but it may be less accuracy. Fortunately, if we adopt the zonotope, this representation can achieve a good accuracy and the computational efficiency. And this is the reason why I choose zonotope as a set representation. Okay, let's go to the second part. That is some preliminaries. Since we adopt the zonotope as the set representation, I'll briefly introduce the definition of zonotope and some of the zonotopic properties. First, a zonotope can be defined by using this equation. We can see that there are many consists of three items: the C, the B, and the H. Here C determines the center and H determines the shape. And B denotes a vector among a hypercube. And the geometrical interpretation of this equation is the Minkowski sum of M segments, line segments, and its center, as we can see from the above three figures. The first one, if M is 1, it can represent a segment of a line. If the dimension is 2, that is M is 2, this zonotope can represent a parallelotope. And if the dimension go more, that is if M equals to 3, this zonotope can represent as this form. Okay, since we consider zonotope has some very less properties. And the first property is called Minkowski sum. That is the Minkowski sum of two zonotope is still a zonotope. There, as we can see from the above figures, the first one, zonotope, plus the second zonotope, and their Minkowski sum is plotted in as this form. So we can see that it can still be represented as a zonotope. Okay. The last property is called linear transformation. That means given a zonotope, its a linear transformation associated with a matrix is still a zonotope, as we can see, and we also can see from the above figures. This zonotope, by multiply with matrix K, it still can be represented as a zonotope. And the next property is called order reduction. That means that for a higher order zonotope, it can be over approximated by a zonotope with less order. As we can see from this figure, for the red one, it can be over approximated by the green one, and finally, it can also be over approximated by the blue one. Okay. Here we consider a subophrasic system. Please keep in mind that subophrasic system consists of two parts: the state dynamic system of physical plants and the remote estimate and controller. As we can see from the right figure, the above is the physical plant, and the lower controller, observer, and detector are remote computation parts. Okay, then by keeping this preliminary in mind, we can go to our today's topic, that is vulnerability analysis. So let's consider our subophrasic system as equation 1. As we can see, it is a discrete time linear time invariant systems. Here, for this system, we have 3 assumptions. The first assumption is AC is detectable and AB is stabilizable. That means that for this plant we can remotely equip our observer and our controller. And the second assumption is that for this disturbance environment noise and the initial state, they're unknown, but they are peak bounded by a zonotope. And the assumption 3 is that this CPS is equipped by a Lomborg-like estimator and a linear feedback controller. We also assume that any choice of L and K, such that A minus LCA and A plus BK are stable is acceptable. Okay. For this subophrasic system, it is equipped with a detector which is also represented by a zonotopic set. As we can see, if we define the estimation error as this form, then its residual signal can be then its residual signal satisfies this dynamic system. And according to this dynamic system, we can finally compute a zonotopic set that means this RK. By using this set, if the residual signal is outside this set, then the detector will alarm, and we know that there have an attack or a fault. Okay, to capture the attack's impact on the system, we can rewrite system 1 as equation 2. Here we can see that the difference with equation 1 is that in the measurement equation, here has an additional item that is FAK. Please note that here F is the attack sensor selection matrix, but it is unknown to system designer. Here we also assume that the adversary knows the system parameters and the adversary has the required resources to launch any suitable attack signals. So by combining equation 1 and equation 2, we can go to the problem formulation. Before go ahead, we are going to define a safe ranging, which is also represented by a zonotopic form that is set X. For this set, it can represent, for example, the constraint of the acceleration and the velocity of our vehicle. The stealthy attacks, here we consider the vulnerability for stealthy attack. So the definition of stealthy attack is it defined as an attack sequence that do not trigger the alarm. Note that the vulnerability are divided into 3 parts. That is, it is possible for CPS to be destroyed, and how to verify the safety of our CPS, and if our CPS is not safe, and how to evaluate the degree of the threat of potential stealthy attacks. And for this 3 parts, we are going to formulate them as by using mathematical language. That is, if we denote the xka as the outer approximation of the reachable set of the state under attack, then we call the CPS is structurally vulnerable if there exists a stealthy attack such that this set is unbounded, and the CPS is vulnerable if there exists a stealthy attack AK such that this set is outer predefined safety ranging, and this set, the CPS is safe if this set is still included by predefined safety ranging X for any stealthy attacks. Okay. First, for the strict vulnerable, it means that there exists a stealth attack AK such that the set is unbounded. And for calculate this set, we should use this dynamic, which it associates the attack signal AK and the difference between the residual signal delta RK. For this dynamic system, by using this system, we can get the conditions for strict vulnerability. That is, this set is unbounded if and only if there exists an eigenvalue, an eigenvector epsilon corresponding to the unstable mode of matrix A, satisfying some ranging conditions. This condition is motivated by this paper, which is published by Professor Mo Yining at 2010. If the readers are interested, I refer you to read this reference. Okay. For vulnerable system, then it means that there exists a stealth attack AK such that the set ZXKA is alter the predefined safety ranging X. So here we need to calculate. So before compare these two sets, first we need to calculate the set ZXKA. This set can be calculated by equation 3. And after calculate this set ZXKA, we are going to compare the containment, compare if this set is contained by the set X. To do this, we should with the help of our lemma. This lemma is published in this reference, which is published in CDC. By using this lemma, we can verify the containment, the zonotope containment. That is, then we can see that the XKA, if the XKA is alter the predefined safety ranging X, it is then the CPS system is vulnerable. Otherwise, it is safe. Okay. If the CPS is vulnerable, we also need a metric to measure the degree of vulnerabilities. Here we use one-sided Hausdorff distance, and this is its definition. As we can see from this figure, it means that for example, here the blue one is the set X and the green one is the set ZXKA. Then the one-sided Hausdorff distance from set the XKA to set X is the distance decay. It means that we inflate the blue one to the green one, such that the green one just encloses the red one. Okay. Okay, then we do a simulation to verify the above mentioned vulnerabilities for this LTI system, and this is its parameters, and we assume that the uncertainty is unknown but bounded, and this is the safety ranging. Then we can see that the eigenvalue, and this is the eigenvalue of matrix A. We can see that all of these eigenvalues are included by the unit circle. Then the set the SKA is bounded. And let's consider the situation that the first sensor is attacked. As we can see from the from this figure, the red one is the set the XK, and the green one is the predefined safety ranging. We can see that it always included by the green one, so it is safe. And here we calculated. Here we also calculated the case that other sensors are attacked. Since here we have 3 dimensions for the measurement. Here we have 7 cases, and there are degree of vulnerabilities. That is the one-sided Hausdorff distance is also calculated. We can see that for the case, we can see that if there are 2 sensors are attacked, for the first and the second sensor attacked, the vulnerability is 3. That the third. Hello?
It seems that we lost some.
Okay. Hello? Can you hear me?
Okay.
Okay. Hello. Now can you hear me?
Yes, please go ahead with the presentation.
Oh, okay. So, please go to the simulation of the vulnerability. Okay. So, from table 1, we can conclude that if we can only protect one sensor from adversaries due to a resource limitation, sensor 2 should be protected, since if sensor 2 is protected, it can be attacked. And as we can see from table 1, the degree of vulnerability is the most minimal. Okay. Go ahead. You go ahead. Okay. Then The next part is do the attack detection for subophrasic system by using zonotope. Here we also consider a linear time invariant system, and we also consider the attack indicates the injected BIOS on the sensor data. We also made the assumption that detectable and stabilizable, and the uncertainty and the initial state are unknown, but peak bounded by lone zonotopes. Here, for the first, here we are going to use two sets, that is predicted state set and measurement state set. The predicted state set is obtained by using the first equation, that by using the system dynamics, and the measurement state set is obtained by using the measurement equation, and this is their definition. And by using these two sets, here our objective is to check if there is intersection between these two sets. Please, yeah. As we can see from this figure, for the first part, for the first figure, for the left figure, there is intersection between these two sets. So this case is attack-free case. And for the attacked case, the set XYK will deviate, and finally, it may reach a point that there is no intersection between these two sets. So this mode, by using this, we can do the attack detection. Before going on, here we need to calculate these two sets. Please note that when there is no attack, this set can be calculated by using a parameterized SK bar. It can include the intersection between the predicted set and the measurement set, as we can see from this figure. Okay, for calculate the set SK bar, we are going to use some set criteria to minimize the outer approximation of SK bar. Here we adopt the segment of the zonotope next figure. Yeah. By minimize this cost function JK, we can finally obtain the gain matrix LK as this form. It can be seen that it is reasonable with the Kalman filter gain matrix. Okay, by using this LK, we can finally calculate the predicted set, and the measurement set can be for the measurement set, it represents the intersection between. It means the intersection. How to say that? Please note that for the S sub-equation that yik equal to cixk plus yik, the corresponding sets can be calculated as xyik. Then the measurement set can be obtained by intersect all these sub-measurement set x, y, k, as we can see from the right figure. Then the predicted set and the measurement set are calculated. Then then we are going to check the intersection between these two sets. And the first, here we are considering two methods. And the first method is called projection method. As we can see, the red one is the predict xk plus 1, and the blue dot line is the sub-measurement set, that is x, y, k. Then we can project the zonotope onto the direction of the onto the direction of the measurement set. We can obtain SZ, and their intersection can be calculated as ST. And the left side is the how to calculation it. But this method has some disadvantages, as we can see. We'll use an example to illustrate it. Here, if the xk minus 1 is the red one, and here we consider two measurements, that is the blue one and the green one. If we use the projection method, as we can see, as we can see, there as we can see, there is no intersection between the predicted set, the red one, and the measurement set, that is the intersection of the blue one and the green one. But if we use the projection method, we can get this conclusion. So the projection method fails. But this disadvantage is overcome by using another method, that is the polytopic conversion. The polytopic conversion, we can convert this zonotope into a polytopic representation. As we know, the intersection of the polytope can can be accurate, can be represented accurately as this form. So by using this, by checking if this set exists, we can know there is intersection between the predict set xk k-1 and xyk. Here we made a simple conclusion. For the projection method, it is very simple, but the performance may be less satisfactory. And for the polytopic conversion, the performance is satisfactory, but it may lead to heavy computation. That is because it will use the polytopic set representation. Okay, then for these two methods, their performance, we also analyze their performance by using a definition which is named the stealthy attack set. It is defined that for given detection method, any set outside the set, any attack outside AK will be detected. Then this set is called the stealthy attack set. Here we calculated the stealthy attack set for the projection method and also for the polytopic conversion method. And this is their calculation. Then we also use a simple example to demonstrate it. As we can see, the red one is a predicted state set. Oh, no, I'm sorry. The red one is the stealthy attack set obtained by using the polytopic conversion, and the green one is a method by using the projection method. So if we inject an attack signal that is the blue dot, then it will be detected by using the polytopic conversion method, but it may not be detected by using the projection method. And particularly, these two methods are effective for false data injection or false data injection attack, but they will fail for the case of replay attack. So to detect a replay attack, we consider injection or noise signal, and this is motivated by the method which is called watermarking. And the difference is that here the injected signal is generated with a uniform distribution. Okay. Then a question arising intuitively is how to calculate the signal we injected. To calculate this signal, we are going to define. We should consider two problems. And the first is by injecting the Lloyd signal. How much control performance will lose. Here, the control performance are denoted by the increased size of the state reachable set xk, and they are calculated by this equation. And the detection performance is defined by the deviation size of the measurement set under replay attack. Where they can also represented by this equation. Then a suitable signal can be obtained by solving this optimization problem. And here delta denote the tolerable control performance loss. Then we use a simulation to illustrate the method, to illustrate our method. This is our system parameters, and the measurement matrix is an identity matrix, and the uncertainties are unknown but peak bounded. And the left figure denotes the skills attack set calculated by two methods, the projection and the polytopic conversion. As we can see, the red one is enclosed by the green one. So the polytopic conversion can achieve better performance than the projection method. Okay, then please note that here AK includes all possible stealthy attacks. So if we inject a signal that is 0.3 and 0.5, we can detect it. As we can see from the figure, it is detected at time instant 100. As we see, the computational time is also depicted in this table. We can see that the time by using the projection is much lower than the time used by using the polytopic conversion. So for the case of replay attack, if we record the signal from 50 to 200 and replay it at 200, the result is the result by inject different Lloyd signal. It depicted from left to right. The left one is the result by inject a Lloyd signal, which is peak bounded by 0.1, and the right one is the result by inject the Lloyd signal, which is peak bounded by 0.3. So we can be effective. And next figure. And we also simulate the case that the recorded sensor data is replayed at different time instant. As we can see from this figure, all of them are effectively detected. Okay, finally, let's go to, and finally, we made our conclusion. The first one is our zonotopic, our subophrasic system vulnerability analysis and attack detection. From work based on zonotopic reachability analysis is established. The capability of stealthy attacks is analyzed. This may be helpful for establishing defense strategy. The detection of false data injection attack and replay attack are considered. Okay, that's all. Thank you.
So Jitao, I'm very happy that we finally managed to get your presentation despite all the technical difficulties that we had at the beginning. Thanks again for your talk, and now your contribution is open for discussion. Who wants to start?
Yes, I can start maybe.
Yes, please, Tarek.
Yeah. Firstly, many thanks for this very nice presentation. Besides the technical problems, but the presentation is very nice. And the topic is very interesting. Please, could you show the slide 16? You have some assumptions on the detectability, 16. I think.
Okay, okay. There are assumptions. Okay.
Yes. The last assumption, so if the AC is detectable due to assumption 1, is it equivalent to, is it possible to find a gain L such that the matrix A minus LCA is stable? Is it equivalent?
Yeah, this assumption is similar to.
Yes.
Pardon?
Is it the same assumption, the first one and the last one?
Oh, no. They are different. The first one means that the estimator and the controller exists. And the last one means that there is no requirement to the gain matrix L and K, or any choice of L, K such that these two matrices are stable is acceptable.
Is it a strong assumption, the last one?
No. It's not strong.
Yeah. For slide 41, do you need some additional conditions such as the persistency of the excitation of the attack?
Pardon? Persistence of
the attack, yes. Do you need some additional assumptions?
Additional assumptions.
Yes, for example, the persistency of the excitation of the attack. Is it required?
No. We do not need this assumption. Because for the attacker, they do not need to know any information of this system. They can record a signal at any time and then replay it.
Okay, so for the attacker, it is not assume that the attacker now can identify the model of the system. So what do you think about this point?
Pardon?
Maybe in some cases, if we record the data about the system, we can make an identification of the system model.
For the system mode.
So maybe we can discuss after about this point. Since your technique is based on fault detection techniques, so how to avoid the non-detection of small attacks which may be hidden due to the presence of uncertainties, for example?
Oh, for yeah, this is the problem. Frankly speaking, currently, this method can detect the false data injection. It is very similar to the fault detection. So both of them have the problem that if the signal injected is very small, this method may fail.
Okay, thank you. Congratulations for this very nice one.
May I ask a question?
Yes, please.
First, thank you for you give us a very interesting topic. And I have two questions to talk with you. May you go to the page 13? Page 13. Okay, thank you. No, 13, not 30. 13. Sorry.
13.
Okay. Yeah. Oh, that's right. From this figure, I know that for SCPS, we have two channels. That is the feedback channel and forward channel. And you only consider the attack on the one channel. So is that deserve us to consider the two channels to be attacked? My question is, why do you consider one situation, the attack only on the sensor, not on the actuals? Can you please?
Okay. First,
that's my question. Yeah.
Okay. First, thanks for your question. Because if there is an attack signal which is attacked on the signal on the control signal, then this signal will bias the measurement signal. Is it right? And finally, to the remote controller, it will have the same effect.
Sorry, there's low voice.
Okay. Can you hear me? Hello?
No, yes, I can now.
Oh, okay. I mean, if there is a signal which is injected in the control, then
Yeah.
it will lead to the BIOS of the plant.
Yeah.
And finally, it will lead to the BIOS of the sensor,
Yeah.
right? And the BIOS of the sensor is equivalent to the BIOS, the attack signal, which is injected as the measurement.
Yeah. That means your method
So that's the reason why I only consider the measurement attack.
Yeah, I get what you mean. Is that mean your method is easily to modify to the situation for the two channels to be attacked? It is easily to you improve your present work to suitable to the situation of the two channels to be attacked.
I didn't consider this case, but I think yes.
Okay, and I have another question. As we know, we have different types of attack. I assume that your method is only applied to the FDI attack. And do your method apply applied to the type of DOS attack? DOS attack.
Yeah, I know denial of service attack. As I see, for me, I only consider the first data injection attack and the replay attack. And for the case of DOS, I may consider it later. And this is the research on time.
My question is, can we use this similar method to detect the DOS attack? Can we?
To detect the DOS?
Yeah.
For the DOS attack, it's very easy to detect. So I don't think there is some. So I don't think it's necessary to do this research by using the tool of Zonotope, because if the DOS attack, it means to block the channel. So if there is signal we can receive, then it means there is no attack. And if we can receive any signal, then it means that we are attacked. So I think this problem is very easy to detect.
You mean that the DOS attack is very easy to detect, to be detected?
Yeah. So I don't. So
okay.
I don't think there is no need.
Okay, that's my questions. Thank you.
Okay, thank you too.
Do we have any further questions? So no one from the audience. Maybe let me ask a question. Could we go please to the slide 32? As during your explanation of this slide, you said you want to reduce the complexity of just this description of the resulting intersection set. And I was wondering, with which techniques do you reduce the complexity? And maybe it would make sense in this case to use some techniques, for example, from principal component analysis in order to reduce the complexity of this matrix H.
For reducing complexity, here this page means that if there is no attack, then there must exist an intersection between the set xkk maps 1 and the measurement set XYK. So during the propagation, how can we compute an outer approximation of this intersection? And here,
yes, and exactly this is my question. How do you end up with an outer approximation that is, let's say, as simple as possible in its description?
Okay. The answer is at the next page. We use we define our size criterion, that is the size of the segment of the zonotope, and then by minimizing this size criterion, we can calculate the G matrix.
Okay.
Sorry, can I add?
And maybe let me just add a second question. When we go to the slide 36, here in your projection technique, you said, or more or less, it's quite easy to see graphically here that the problem is that you're always intersecting, for example, the red area with the green one, the red area with the blue one, and not the green with the blue one. So the question is, first of all, would it make sense to check first of all the measurements and then do the projection? That's my first question. And the other question is, I think detecting this scenario as something where you have the attack would be quite easy using techniques, for example, for feasibility analysis of linear matrix inequalities.
Pardon? For your first question, do you mean?
Yes, first intersect green with blue.
Yeah.
Perform a rotation of the red area in such a way that it becomes more or less parallel to a new coordinate frame, just in the direction of the principal axis of this red area. And then you immediately see that a projection of the intersection is outside. And I think that's more or less just reversing the order of your intersection operations. As maybe that's something to consider for future work.
No. for the projection method, its computation is very easy because if we project the red one to the direction of the green one, then we can only need to compare two interval.
Yes, I agree with this.
Can you get my idea?
Yes, I agree with this, but I think the problem of your description at the moment is just the choice of the coordinate frame in which you perform the projection. Because if you, let's say, rotate the axis, the black axis, by 45 degrees in your graph, you would immediately see rotations are linear operations in this case on your zonotope, and therefore you would immediately see an empty intersection. Yes, and the other thing is just, the other thing that I just said is more or less an idea for an outlook. Because when someone is using computational techniques for solving linear matrix inequalities, there's usually some feasibility check applied. And such kind of feasibility check could detect this scenario as something where you don't have a common intersection of red, green, and blue.
Red and blue.
Of all three colors. But I think that's something where you should have a look at literature for solving linear matrix inequalities.
Okay. I didn't consider this problem.
Yes, because on the next slide, you immediately see that this polytopic representation is a matrix inequality, a linear one. This formula in the curly brackets. That's an LMI.
No. It's not an LMI.
It is an LMI in X.
I think that
during this inequality, it's linear programming without
yes, linear programming. Simple linear programming.
Yes, it's simple linear programming, and using tools for linear matrix inequalities, you can show that this is infeasible. I'm almost sure that this works immediately. Okay.
Yes.
Further questions?
Okay, actually, I just want to emphasize on this formula, just to add a little bit. And I think that this formula, but I think it's just on the slide, is wrong. I mean, Q sub y should be on the other side, and Q and lower Q should be on the other side of the equation. So that should be the intersection of the polytope.
Yeah. Thank you for your for pointing out this problem.
Yes.
This is my typo.
Have you checked the Zonotopic Kalman filter? Because actually many of the concepts that you are using are related with this. Actually, regarding the question of Tarek, he said something about the last assumption, and I actually agree with him, because basically assumption 3 is a natural consequence of assumption 1. I mean, you shouldn't assume assumption 3 because it's already implied on assumption 1. I mean, if you have a stability detectability system, this system is for sure you can find a constant that makes this system stable. I mean, that's the constant of stability. And you are using the output, and you said already that it's detectable, so you don't need this condition. I mean, assumption 3 is just a natural consequence of assumption 1. Yeah.
Yeah.
Just,
yeah, you are right. If assumption 1 is satisfied, then assumption 3 is it also it also can be achievable.
Yes. One last thing. The value of L, Compastel used something that is called the F radio, and he used the Frobenius radio, and he optimized using the Frobenius radio. So maybe this can give you a better performance. So because you already find the optimal for this case, and maybe you should take a look. But I think it's a really, really nice presentation. Thanks.
Okay. Thank you. Here, I would like to point out that here I made assumption 3 only to point out that the matrix L and K are predefined, and they will not influence the definition of vulnerability, and that's my purpose.
Yes, maybe since we already have the slide here on the screen concerning the structure of this estimator, I think that's not the classical definition of a Lünberger observer. Because for Lünberger observer, you would have in this round brackets in the assumption 3, you would have the difference between yk and the corresponding output.
Yes.
What's the reason why you used a version that is shifted by one time step?
That is during the field of CPS, I found that many assume that the estimator is equipped as Kalman filter. So, so if I shift the Lombrick one-time instant, it may be easy to compare the case with the Kalman filter.
Okay, is this more or less a philosophical question?
Okay.
How to define a stationary Kalman filter? Because you could write it up as the result after the innovation step or after the prediction step. Is this more or less philosophical?
Yeah. It can be regarded as a stable Kalman filter.
Okay, any other questions from the audience?
I want to ask, what is strange notation for the zonotopes? To my mind, it interferes with popular notations for the scalar product. Well, angle brackets.
Hello.
Do you hear me?
Pardon, can you see the question again? I can't hear you.
This maybe not a question, not a real question, but a remark. Why do you use such a strange notation for the zonotope? Angle brackets. It interferes with the popular notation for the scalar product.
Notation.
Yes, scalar product. One of popular notation for the scalar product in Euclidean spaces is angle brackets. Yeah.
This definition is quoted from
the scalar product of C
from the dissertation of Professor Hausdorff.
Yes, I understand, but the notation for the scalar product that I mean is very, very popular. It is a classical notation. Well, consult textbooks, for example. And this record resembles scalar product of C and H.
Because by using this dilution, we can simplify the definition.
No.
Because a zonotope is just influenced by its center C.
No. I mean symbolic notation, your symbols used for the
just use something else than this triangular brackets.
Yes.
For example, double lines, for example, or something.
CH, zonotope generated by C and H. Because this notation will show, for example, your algebraists, your experts in numerical optimization, and so forth.
Okay, before we come to the end of today's seminar, another question came to my mind. You mentioned, I don't know which slide this was, around slide 30. You mentioned something concerning the controllability of attacks. No,
Controllability of attacks.
Yes, you had some controllability matrix that showed that you can excite. No, it's not this slide. I think it was something around. Let's go to the slide 28,
Okay,
and then we can browse.
Slide 21.
No, something around 28.
You mean slide 21?
Is it 21? Let's see. Ah, yes, that's this one. The controllability matrix there. This condition for vulnerability. You can certainly evaluate this controllability matrix, and you can check whether it is controllable or not. But classically, for example, using Kalman's criterion, you don't get anything concerning a degree of controllability. Would it make sense, for example, to compute the controllability gradient here in order to figure out how strong or weak the vulnerability is? Because this gives more or less an absolute value on the degree of vulnerability.
Note that this condition is made for the strict vulnerable. It means that we can inject a signal AK such that the item delta EK go into infinity. So
yes, it's a structural result
if we
that
want
says
to
yes or
achieve
no.
this result.
Yes, it just says, is it vulnerable or not? It's just black and white. But you don't get anything concerning the degree of vulnerability. Are you close to the border of vulnerability or not? And I think this closeness to the border between vulnerable or not could be checked by using the gradient. It's just a classical result of controllability analysis.